Applied Math on Tuesday. We are nearing the end of our linear applications, means the word problems. Yesterday, we completed a table of values. Just to recap, this unit is all about linear functions, straight lines, and we use straight lines to model lots of situations in our day-to-day lives. Right? So lots of things happen that we observe in our day-to-day life in a linear fashion. And that means when we collect all the data and we graph it, the data shows a straight, like a relatively straight line, either moving up or downwards. We can either be given the equation in a math problem, or we have to develop the equation ourselves, which is maybe a little tougher. And to develop the equation ourselves, we have to have a table of values. Yesterday, we were given a table of values that was half done for us. Today, I'm working on page 34, example 5. This is maybe the tough type of question to do. This is developing a table of values just from information given in the description of the problem. So let's take a look at this description. It says, there's 8 centimeters of snow on the ground. It's melting at a rate of 0.5 centimeters per hour. Complete the table shown below. And they don't give us anything to start with. So we have to look at the story and just kind of develop, I guess, a sense of what's happening. Now, first of all, the very first sentence says there's 8 centimeters of snow on the ground. So at time 0, which is right now, before any time has passed, just when they're starting, there's 8 centimeters of snow, right? It rates at a melt of 0.5 centimeters per hour, okay? So after 1 hour, melting means the amount of snow is going down by 0.5 centimeter. So I'm going to have 7.5, right? In 2 hours, this will bring me down to 7 centimeters. In 3 hours, 6.5. Notice I'm going up. I'm just going up hour by hour. I could go up by 2 hours or 4 hours, but I'm keeping this simple so I don't lose track. And it just makes my my table filling quite a bit easier. But again, you can use any numbers you want on the top as long as they're positive numbers, right? Because we can't go backward in time. So I've got my time. I've got my amount of snow. It says create a scatter plot. That just means point these plots, right, of the data that I created. I used quite small numbers, makes it easy to graph. Remember, this is my x-axis, this is my y. And if they don't tell me to use other variables, I'll stick with x and y because it makes things just easier to graph and easier to put into my calculator. Because once again, the calculator only uses x and y. All right, so I have to go 0 to 4 centimeters. So that's kind of nice to show. Okay, so this is just 0, 1, 2, 3, 4. I can go up to 5 if I want. And now let's see, I'm starting at 8 and I'm dropping. So this tells me my line is going to be decreasing, correct? So I just need to go as high as 8. So I might do 2, 4, 6, 8. I might go up by 2s. Notice I don't need to use the same scale on the top, the bottom axis and the vertical axis. As long as I keep my scales consistent, whatever I started with numbering on for my first notch, I have to be consistent along the horizontal axis. And if I used a scale of 2, I have to use a scale of 2 all the way up the y-axis as well. All right, so I'm going to plot my points. I don't need my graphing calculator for this, right? At 0 hours, I'll have 8 centimeters of snow. At 1 hour, 7.5. Well, halfway between is 7, so it's going to be about here, right? At 2 hours is 7. 3 hours is 6.5. Oh, it's getting a little tough, right? 4 hours is 6. Could have probably used a different scale. And this is my scatter plot. A scatter plot is just the dots themselves plotted, right? So I can see it's a decreasing line. Is the line linear? Yeah. Is the relation linear? Yes. Because it's trending downward. Yes. The data, the straight line pattern, falling to the right. And that means as I move across the page from left to right, the dots are going down, descending, falling. How long will it take for the snow to melt completely? All right, well, this is where I'm going to use my graphing calculator to answer that, because for the snow to melt completely, it would have to be right down here. So I'm going to do, and they asked me for the linear regression equation, right? So now I have to do my linear regression equation, and I get that from my graphing calculator. So the steps have been told to you many times, and it's on page 13. So whoops, turn my calculator on. I cleared my calculator out earlier. So in stat edit, I'm going to put my x values in. And then I'm going to put 8. You have to have the same number of y values as x values, entering coordinates in. And even if you had done this question without me and you had started, maybe you were going up by 2 hours, every 2 hours, and you use different data entry points, we'll still get the same regression equation because we're modeling the same situation, right? So whatever data points you used, as long as you're using the right ones appropriate to the situation, we're going to get the same regression equation. All right, so remember where we go from here. I think I'll set my windows, and my windows are, well, this is just a quadrant 1 graph, so I'm going to put zeros in for x min and y min, and I think if I keep it at tens, it's probably okay. Let's take a look at this graph. Oh, I have to turn my scatter plot on, right? And then take a look at my graph. Sure enough, that's what I see here. All right, so if I just left it like that and just entered my data in under stat edit and hit graph, I would just see these dots, right? Make sure you put your scatter plot on, turn it on. Remember under second y equals, make sure that it's on, not off. And then you have to turn it on to see the dots. Now, if I just left it like this, I don't have the equation, right? I have to develop the equation to answer further questions. And that's where I go to stat calc. And that gives me my equation of a linear. I choose number 4. Then we get this familiar screen. Remember, you move down to storing your equation. And that's where you stop and you press vars, y vars, enter, enter, enter. And it gives you your a and your b value to substitute in the right spot in the equation. So my equation will be y equals negative 0.5 is my a value times x, and my b value is 8. Okay, so that's my linear regression equation. That's what they asked me for part B. Now, when you pressed remember when you pressed the vars, y vars, or pardon me, stat calc number 4, and then you pressed the vars. When you stopped here and pressed the vars, the y vars, equal, 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 and you got this window, as soon as you get this window, it also pastes the equation in your y equals screen. Once you have something in your y equals screen, remember that's what you need in order to create that line. In those questions on the previous lesson where we were given the equation of the line and we can just enter it in here, we bypass creating a table of values. We get that line created directly into our calculator. As long as you have something entered into your y equals statements, you'll have the line showing up. Okay, so there's my straight line going through. And once I have the straight line running through the dots, I can answer any further questions that the problem may have for me. So let's see what the problem is saying now. How long will it take for the snow to melt completely? Well, this would be the snow going down to 0, right? So if you think about it, this line, what do I want? Well, I want this. When y becomes 0, that's going to be my x-intercept, right? That will tell me the number of hours. It's way over here somewhere. So basically what they're finding me are asking me is find x when y would equal 0, right? Y equals 0. Well, if we're finding x and we're given a y value, remember what you have to do there? You enter into your y equals screen. I'm going to keep focusing. I keep this line in. I enter a new line, y2 equals 0. And I can't see it. It's over here somewhere. So I want my x-intercept. I'm going to increase my x windows. They're set at 10 now. I'm going to put 30 in to see if I can see my, there. Because this is the spot I'm looking for, right? This is my y1 statement. This is my y2 statement, y2 equal to 0. Now I'm going to go second, trace number 5. This is how I find all my x values. I have to use that system and take a guess. Okay, when y is 0, when there's no snow on the ground, x is 16, so that's 16 hours. Okay, x equals 16. This means in 16 hours, there is 0 centimeters of snow. When will the snow melt to a depth of 3.5 centimeters? Okay, so again, we're asked to find x, but this time when y equals 3.75. Okay. It's the same style of question, finding x when you're given y. So when I'm given y, I go to my y2 statement. Now I'm going to erase 0, and I'm going to enter 3.75 in. This time I'll see my 2 lines, right? Line 1, line 2. The reason I couldn't see line 2 before, it was lying right on top of the x-axis. All right, same procedure. Second, trace, number 5. I'm going to move my cursor to where the crossing is. There. Enter, enter, enter. So when y is 3.75, x is 8.5. Okay. X equals 8.5. In 8.5 hours, there will be 3.75 centimeters of snow. Now, asks us a question. Part E, what are we assuming about our answers to C and D? Well, we're assuming that this, do you see this line is going down at a very steady, regular rate? We are assuming that the snow keeps melting at the same rate. Now, what would cause it to not melt at the same rate? Well, maybe if the sun came out and was very warm and the temperature rose, maybe it would start melting quicker. Also, I think there's something else we could add in. We are also assuming that it doesn't snow anymore. Okay, because if it started snowing again, the snow would start piling up, right? So those are 2 big assumptions. You might think of another assumption. There may be other assumptions. I can't think of any more at the moment. But the big one is that we're assuming when we use a straight line to model things, we're assuming that the rate just keeps this the same. I mean, another thing that might affect it is the wind. If the wind picks up, that might make the snow melt faster because it's agitating the snow. All right, that's example 5. Let's take a look at example 6, and then I'm going to assign some more homework for you maybe. Example 6 is, it's not really creating, it's actually just understanding graphs and windows a little bit. Let's take a look at number 6. Using appropriate graphs for applications. A rocket follows a path given by this equation. So this time they're giving us the equation, right? So it's always nice when they give us the equation and we don't have to generate the equation ourselves using a table of values. X represents the distance from the launch pad and Y represents the height. Okay, so this would be the X. I think it would be the X and the Y. This is the X-axis, the Y-axis. Okay. 2 graphs are drawn. They both represent this equation. Both graphs show the equation accurately, but the second graph fits the situation better. Explain why. Okay, well, the explanation is down here, right? Note that the domains and ranges of these 2 graphs are different, although they use the same linear function. So this is representing the same thing. Definitely graph 2 is better, right? This is better. And the reason it's better is when we're talking about the distance, so the rocket launcher, I guess, is sitting on top of a launch pad that's 8 meters from the ground. And then the trajectory forces the rocket up into the sky. And as it's moving to the sky, it's actually moving kind of like an airplane too, right? It's moving up, but it's moving across the Earth as well. So this is definitely the better graph because this is a quadrant 1 situation, right? And it says down here, the domain and the range of graph 2 is restricted. And we call it, when we use just quadrant 1, we call it restricted because the rocket is only moving forward and it's only moving up, right? This is, I call them quadrant 1 graphs. Because the rocket is only traveling positive distances, right? The rocket is not traveling backwards and it's not traveling into the ground, under the ground. The rocket is traveling up into the air and it's traveling across the Earth, right? So if you're only dealing with positive quantities, it's a quadrant 1 graph. And in applied math, many of our graphs are quadrant 1 graphs. So that's something to keep aware of. And that's many of, when you have your little grid drawn, many of the little grid drawns are just drawn in a quadrant 1 graph, okay? Let's see. I think we could talk about example 7, and then I think I'm going to give the next couple of days just as work periods. This is a very big assignment coming up, especially if you're working through your graphing calculator software. So let's take a look at this last example, and then I'm going to call it a day. Please make sure that you write into the email or hop onto the live chat if you have any questions for me during class. Let's take a look at this last application. So it's still a linear, but this time they gave us the equation, right? When they give you the equation, I think these are probably the easiest to deal with, right? Because you don't have to create a table of values. The only thing you have to worry about is your windows a little bit, right? So turn your calculator on or get your computer software cleared up. Clean out your memory. Do a second plus sign number 7, number 1, number 2. All right, now we've got this equation. H is that, now this time they're using V for Y and H for X. Okay, so they're using different variables for X and Y, so I just have to use the variables they give me, right? Let's see. H is the horizontal distance and V is the vertical distance. So this is just like that rocket ship question. Okay, so this is the vertical distance. In meters. And this is the horizontal distance in meters. Okay, draw the graph of this situation. All right, so I'm going to enter this into my calculator. Just going to keep adjusting the focus, so hopefully there. In my y equals, I'm going to enter in negative 3.5x plus 12.5. Let's see what this graph looks like. So I do see the x-intercept, but I don't see the y-intercept, right? Or I guess the v-intercept. So I'm going to increase. Now up here, that's your y max, right? I'm just going to increase my y max. How about if I increase it to 20? Let's see what that does. Okay, so that's nice. I see my y and my x-intercept, so that's good enough for graphing. Now I have to, if I could just figure out, because this is a downward and negative correlation, if I can just plot the x and the y-intercepts, that should be good enough for my graph. So remember to find the y-intercept, second trace value, put a 0 in for x, and sure enough, it's 12.5. So that's 12.5. And now let's find the x-intercept. Same as always. Enter into the y equals screen, y2 equals 0. And then second trace again, number 5, intersect. And I want to find this intersection point, right? Okay. Enter, enter, enter. So when y is 0, x is 3 so I'm just going to put that here. I'm not really worrying about scale because I'm just putting one number on my x, one number on my y. So I can say that this is my scale. My scale is 12.5 and my scale is 3.57. I'm not extending my line beyond quadrant 1 because this is a quadrant 1 graph, right? I can't go. This is a ball being dropped off a roof. The ball starts at a height of 12.5, and then when it hits the ground, that's it, right? The experiment is over. It doesn't go deep into underneath the ground. Okay, what does H represent? Well, just like that previous question, the ball is being dropped off and it's heading towards the ground, but it's also heading out. So H represents the distance the ball moves horizontally from the building. It's thrown off the rooftop of a building. And that's the horizontal distance that it travels, right? It travels a horizontal distance this way, as well as a vertical distance down. V represents the vertical distance. The ball travels. So in total, the vertical distance it traveled was 12.5, right? And horizontally it traveled 3.57. What does the v-intercept represent? Well, it represents the height that the ball was dropped at. The height, I guess the height of the roof, right? The height the ball was dropped from. And what does this point represent? Well, it represents the distance from the, I guess, from the base of the building, because this would be the building, right? To where the ball landed. How far from the base of the building did the ball land? Well, 3.57 meters. Does the graph continue forever and ever in both directions? No, that's why I stopped it here and stopped it here. No. The ball started at a height of 12.5 meters and ended at a height of 0 meters, right? That's it. It didn't go higher than 12.5. It didn't go lower than 0. Also, the ball started at a horizontal. Okay, so it started here, right? That was a horizontal distance of 0. 0 meters and ended at a horizontal distance of 3.57 meters. Okay, so it ended here, right? It didn't go any further out. That's it. It ended here and it stopped. What are the limitations on the value of V? Well, they're basically asking you the range, right? This is known as the range. The domain and the range, remember? The range is the vertical, all the possible vertical numbers for the question. And the domain is all the possible horizontal numbers. So vertically, we said this graph is limited from 12.5 to 0, but we always write the small number first. So we say 0 to 12.5. Okay, and I enclose them in these brackets like that. The limitations on H, this is known as the domain. Okay, so the domain is from 0 to 3.57, and that's it. And then after it, when it hits 0 meters, when it hits the ground, the experiment's over, right? That's it. The question's over. So there's no need for any further values for the domain than from 0 to 3.57. And vertically, there's no need for any more values other than from 0 to 12.5. So that's it. That's the domain and the range. Okay, so I did 3 examples, which is a little more than I was hoping, than planning on doing, I mean. I am going to get you to start working on assignment 6. It's a big assignment and it takes a long time because you're either entering equations in or you're entering, I think I assigned 1 to 4, right? So finish up assignment 6. You're either entering equations in or you're entering tables of values. And each time you do that, you have to clear your calculator out. So applied math does take longer in that regard. Continue on with assignment 6. I'm going to have a work period tomorrow for sure. Let me know if you have any questions today as well. You can email me. You can enter the live chat if you want. But tomorrow I'm just going to open up an open to Google Meet so you can ask me questions during tomorrow's class. So hopefully I will be talking to some of you soon.